Hello everyone, welcome to AS Online. Myself, Professor Rajendra Gharashe. I have done M.Tech from India Institute of Science, Bangalore. I was the All India 7th ranker in the GATE examination and I am working as a faculty member at AS Engineering Academy. So in this session, we are going to discuss revision session and important question analysis of the subject Power Electronics for TSPSC AE, okay, diploma level questions, okay. So in short, we are going to revise all the concepts and we are going to solve some important questions, alright, yeah. So let us start with the syllabus. So in the syllabus they have given basics of power electronic devices and the devices they have added are SCR, that is silicon control rectifier, TRIAC, DIAC, GTO, UJT and IGBT, okay. So only we are having the study of these devices, but as long as the syllabus is considered, you are having the detailed analysis of SCR, whereas all other devices you are having only introductory part, okay. So for all these devices, yes, you are having construction, working principle, next characteristic, advantages, disadvantages, applications, okay. And for the SCR we are having the protection mechanism as well, okay, right. Next, so this is the first chapter, that is the basic of power electronic devices, okay. Next, converters. Converter means AC to DC converters, that is a rectifier, okay. So in the second chapter, that is a converter chapter, we are having uncontrolled rectifiers, controlled rectifiers, half wave rectifier, full wave rectifier, okay. 3-phase, half wave, 3-phase, full wave, also in the case single phase half wave, single phase full wave. In addition to that, you are having the semi converters as well, okay. Next, inverters. Inverter means input is a DC, output is a AC, okay. So in this chapter you are having single phase half bridge inverter, single phase full bridge inverter, okay, pulse width modulation techniques, next 3-phase inverters and a current source inverter, okay, only introductory part. Next, AC voltage regulators. Input is a AC, output is also AC, okay. AC voltage regulators converts fixed AC to variable AC. Input is also AC, output is also AC, but the frequency of the output and frequency of the input both are same. So AC voltage regulator gives output in terms of only variable voltage. Frequency is the same, frequency is the same, okay, right. Next, in AC voltage regulators we are having integral cycle control, single phase half wave AC voltage regulator, single phase full wave AC voltage regulator, okay. You can say AC voltage regulator or AC voltage controller, both are same, right. Next, choppers. Choppers is the circuitry, chopper is a circuitry where input is a DC, output is also DC, okay, but output is a variable DC. Input is fixed DC, output is a variable DC, okay. In this chapter you are having step down chopper, step up chopper, step up, step down chopper, okay. And similar to that of these three chopper circuits, we are having buck converter, boost converter and buck boost converter, only diploma level, okay, very simple questions, okay, we will discuss. Next is the cycloconverters. Cycloconverter is also known as a one stage frequency changer. Specifically, these converters are used to get the variable output side frequency, okay. Strictly speaking, cycloconverter gives output in terms of variable voltage, variable frequency, but most of the cases we are using it as only frequency changer, only frequency changer. Next, speed control of AC and DC motors using power electronic devices, that is the AC and DC motor drives, okay, applications of power electronic devices, okay. So in the syllabus you are having basics of power electronic devices, or you can say power semiconductor devices, this is the first chapter. Second is a AC to DC converter, that is a rectifier. Third is a DC to AC converter, that is the inverter. fourth is AC voltage regulator, chopper, sixth one is a cyclo converter, and the last chapter is a drives, okay, DC and AC motor drives, okay, right. So let us start with the first chapter, power semiconductor devices, okay, power semiconductor devices. Now, so they have asked us some simple questions, okay, on semiconductor devices. So very first point is classification of power semiconductor devices. So power semiconductor devices are classified based on the various parameters. So first one is a driver circuit used in the device. Based on the driver circuit used in the device, there are types: voltage controlled and current controlled devices. In the next is a carrier used in the device, that is majority charge carrier or minority charge carrier devices, okay. Next, number of terminals in the device, 2 terminal, 3 terminal or multi-terminal, okay. Next, triggering methods, whether it is a pulse triggered, whether it is a level triggered, edge triggered, etc. Next is based on the polarity of voltage blocking, that is either whether it is a unipolar or a bipolar. Next is based on the direction of the current conduction, whether it is a unidirectional or bidirectional, okay. So let us discuss one by one. So first is classification of power semiconductor devices based on the driver circuit used in the device, okay. So based on the driver circuit used in the device, there are two types: current controlled, or it is also known as a current driven, and second one is a voltage controlled, or it is also known as a voltage driven, okay. So they have asked the question, simple questions: which of the following are voltage control devices, which of the following are current control devices, okay. So if you check, in a current control devices, we are having a GTO, that is a gate turn off, and a thyristor, that is a SCR. Thyristor means SCR, okay. SCR or thyristor and GTO, these are the current controlled devices. Strictly speaking, your SCR is a charge control device, but most popular method of triggering of the SCR is a gate triggering. So that's why it is also known as a current triggered. Second is a voltage controlled or voltage driven devices. Here we are having the voltage control devices like MOSFET, IGBT, SIT, MCT, right? Static induction thyristor and MOS capacitor thyristor, okay. So these are your voltage controlled devices, voltage controlled and current controlled devices, okay. Next, classification of power semiconductor devices based on carrier used in the device. So majority charge carrier devices, minority charge carrier devices. Majority charge carrier devices were having only MOSFET and SIT. This SIT is not there in your syllabus, so forget about it, okay. So only MOSFET you are having the majority charge carrier devices, whereas all other devices you are having, those are minority charge carrier devices. Means your power diode, your thyristor, GTO, IGBT, etc. all are minority charge carrier devices, okay. Next, they have framed the questions, so simple questions they have framed. Next, classification based on number of terminals. So 2 terminal devices and 3 terminal devices, simple we know, okay. So your diode is a 2 terminal device, whereas all other devices, your thyristor family and transistor family devices, all are 3 terminal devices, okay. Transistor family means power MOSFET, power BJT, IGBT, these 3 are transistor family devices. Thyristor family devices means silicon control rectifier, that is SCR, right. Second one is your TRIAC and GTO, these are your thyristor family devices, okay, right. So your thyristor family and transistor family devices are 3 terminal devices, okay, and 2 terminal devices are only diodes you are having, okay, only diodes. Next, classification of power semiconductor devices based on triggering methods, okay. So pulse triggering and level triggered devices, okay. In a pulse triggering we are having SCR, GTO. We know SCR and GTO, once they turns on, after that if I remove the gate signal, then also my SCR will continue into the on state, na. So very small pulse is required to turn on the devices, so that's why it is a pulse triggered. Whereas if you check all other devices, your transistor family devices, if I want to maintain the transistor family devices in a on state, then I need to maintain the controlling signal continuously, okay. In case of power BJT, we need to circulate the base current continuously to maintain BJT in a on state. So these are not the pulse triggered, be careful, okay. So your transistor family devices are your level triggered devices, okay, whereas SCR, GTO, these are the pulse triggered devices. All right. Next, classification based on the polarity of voltage blocking. So based on the polarity of voltage blocking, there are two types, unipolar and bipolar. Unipolar means what? A switch is said to be unipolar, or a device is said to be unipolar if it blocks either forward voltage or reverse voltage during its off state, okay. So if the switch blocks only forward or reverse voltage when it is in a off state, then it is known as a unipolar. And if switch blocks forward as well as reverse voltage during off state, then it is known as a bipolar. So which are the bipolar devices we are having? We are having the thyristor and GTO. These are the bipolar devices. Apart from that, we are having triac. Thyristor means I am saying SCR, okay. Triac is also bipolar device, and all other thyristor family, all other transistor family devices are your unipolar devices, okay. So I am writing transistor family devices are unipolar. Transistor family devices are unipolar, okay, right. So they have asked some simple questions, right. So this is for your information. Next, classification based on the direction of current conduction. So there are two types, unidirectional, bidirectional. Triac is your bidirectional device, okay. Triac, here it is, triac. And here one more thing I have written, RCT, that is a reverse conducting thyristor. Reverse conducting thyristor is not there in your syllabus, so forget about it, okay. So only triac is a bidirectional device, whereas all other devices are your unidirectional device, okay, only unidirectional devices. So next, so here some important information table. We are having the devices like SCR, GTO, BJT, MOSFET, IGBT and triac. SCR is used for high power capability and low switching frequency applications, okay. So if they ask for high power, low frequency, which device is preferred? Your SCR, okay. Next, for high power, low frequency, GTO is also preferred. Next, power BJT for medium power and low switching frequency applications. Comparatively, the on-state power losses in BJT are high, so they compared to that of your SCR. So therefore, BJTs are not preferred for high power applications, right. So it is having the limitation up to only medium power applications, and switching frequency is a low. Power MOSFET, low power applications and high switching frequency applications. MOSFET is totally opposite to that of your SCR, be careful. This is a majority charge carrier device, MOSFET. SCR is your minority charge carrier device, okay. Next, IGBT. IGBT means insulated gate bipolar transistor. IGBT is a combination of MOSFET and BJT, okay. So it is preferred for medium power applications and medium switching frequency applications, okay. And triac is for low power and low frequency applications, okay. Next, whatever the devices we are having available till now in our real life, okay, which device is having a highest switching frequency? Then your MOSFET is having a highest switching frequency, right. So in some of the examination they have asked the question, for application of 100 kilohertz switching frequency, which of the following device is preferred? So always keep in mind, if your switching frequency is greater than 50 kilohertz, then we need to go for only MOSFET, okay. I am writing here switching frequency, let me write switching frequency of different devices. I am writing here, right. BJT, that is a power BJT, switching frequency is up to 20 kilohertz. IGBT, switching frequency is up to 50 kilohertz. And MOSFET, switching frequency is up to 1 megahertz. So MOSFET is having a highest switching frequency. Okay, so they have asked the question. So please keep in mind, if they give the switching frequency greater than 50 kilohertz, your answer should be only MOSFET. Only MOSFET. All right. Yes. Next, let us have a look on SCR, silicon controlled rectifier. Okay, we know SCR is a device which is having a 4 layers and 3 junctions. Okay, so here it is a construction of the SCR. We are having 4 layers, P1, N1 minus, P2 and N2 plus. Okay, this is a lightly doped layer, and in power electronics devices or power semiconductor devices, this lightly doped layer is intentionally added. Why? What is the purpose of this lightly doped layer? Because of this lightly doped layer, your device voltage rating increases. Your device voltage rating increases. Okay, so that is the main thing. Next, so first layer, second layer, third layer and fourth layer. 3 terminals, anode, cathode and gate. How many junctions we are having here? 3 junctions. This is the junction J1, junction J2, junction J3. Alright. Here it is a symbol of the SCR, anode, cathode and gate. Okay. Between anode and cathode, of the SCR, there is a load circuitry, right? High voltage, high current circuitry. And whereas the between gate and cathode terminals, you will be having the controlling circuitry. So here we are going to connect the elements and we are going to form the circuit. This circuit is used to control the operation of your SCR, silicon control rectifier. Next, some important points. When SCR is in a forward bias mode, SCR forward bias mode means anode is at a higher potential than that of the cathode. When SCR is in a forward bias mode means anode is at a higher potential than that of the cathode. Then how many junctions will be in a forward bias mode? They have asked the question. Okay, so always keep in mind, if anode is at higher potential than that of the cathode, the meaning is it is like between anode and cathode we have connected the external supply, and positive plate of the supply is connected to the anode, negative plate of the supply is connected to the cathode, right? So it is like external supply I have connected, positive plate is connected to anode, negative plate is connected to the cathode. Now anode higher potential, cathode lower potential means from anode towards the cathode, your potential is decreasing. Means this P1 layer is at a higher potential than that of N1 minus. N1 minus is at a higher potential than that of the P2. P2 is at a higher potential than that of the N2 plus, right? Like this we are having. So tell me, if P1 is at higher potential than that of the N1 minus, means this junction J1, which is a junction between P1 and N1 minus, this junction will be in a forward bias mode. Okay, so if SCR is in a forward bias mode, then J1 forward bias. What about J2? Compared to P2, N1 minus potential is higher. Now in PN junction, if P-type layer potential is lesser than that of the N-type, means your PN junction will be in a reverse bias mode. Okay, so J2 is in a reverse bias mode. And similarly, you can check J3 forward bias mode. So if when SCR is in a forward bias mode, then junctions J1 and J3 will be in a forward bias mode, whereas junction J2 reverse bias, right? J1, J3 forward bias, J2 reverse bias. Okay. Next, so the junction J2 will not allow your SCR to continue to the conduction mode. So in order to turn on the SCR, what we are doing? We are circulating the gate current in this gate cathode circuitry. Okay, and my SCR will turn on. Right? Similarly, tell me, if SCR is in a reverse bias mode, SCR reverse bias means anode lower potential, cathode higher potential. Then your junction J1, J3 reverse bias, J2 forward bias, completely ulta of that this one. Okay, opposite to that of this one. Next, yeah, biasing of SCR, just now we discussed the forward biasing, reverse biasing. Okay, next is static VI characteristics of a SCR, important one. Okay, so you might have come across this type of characteristic of SCR. Okay, now, so this is the plot between voltage across SCR, current flowing through the SCR, right? So in this characteristic, we are having the three modes. They have asked the question. We are having the three modes. This OM curve indicates forward blocking mode. OM means what? Forward blocking. Forward blocking mode means your device is in a forward bias mode, but it is in a off state. It is in a off state. Okay. So forward blocking mode means voltage across device is a positive, right? It is a non-zero voltage. It is a positive voltage. It is a high voltage, and current flowing through the device is very low. Current flowing through the device is very low. Any operating point you can check on this OM curve. Current value is very low. Current value is very low, but voltage value is high. Voltage value is high, right? Second, this NK. Let me indicate this as N here, and this is K. NK indicates forward conduction mode. NK is a forward conduction mode. Forward conduction means device is in a forward bias mode and it is in a on state. Okay, so you can check any operating point on a NK curve. The voltage across device is very low. Current flowing through the device is high, right? High current, low voltage. So it is a forward conduction mode. And next one is a OP. This curve OP, it indicates reverse blocking mode. OP indicates reverse blocking mode. Right? Reverse blocking means device is in a reverse bias mode and it is in a off state. In SCR, we don't have reverse conduction mode. We don't have, I am saying. Okay. So only three modes are there: forward blocking, forward conduction, and reverse blocking. Only these three modes are there. Okay. Right. Next, again we are having latching current and holding current. Right. Latching current is current which is associated with the turning on of a SCR. Holding current is a current which is associated with the turning off of a SCR. Okay. Generally for SCR, latching current is greater than the holding current. Okay. In real life, we are having latching current is always greater than the holding current. Based on this also, they have asked the questions, right? So latching current is always greater than holding current value. Next. So two transistor analogy of SCR. We know SCR is a PNPN device. Okay. And we represent that in form of two transistors. How we have divided SCR into two transistors? It is PNPN structure. We are going to divide as a PNP and NPN. You might have come across this type of structure. Right? P1, N1 minus, P2 and N2 plus. Anode, gate, cathode. Right? So, if you join these two structures, you will get the PNPN structure of your SCR. Okay? Right. So, how we have divided? It is divided as PNP and NPN. PNP and NPN. Generally, this two transistor analogy is used to understand how the device turns on by using the gate triggering. Okay, simple. Next, protection of SCR. So, as long as the SCR protection is considered, we need to protect it against over voltage, over current, dV by dt, that is high dV by dt, and high di by dt protection. Okay, right. So, how to protect SCR against over voltage? For that, we are using the varistor, right? We are using varistor. So, this is the varistor which is connected across SCR. which is connected across SCR, either varistor or you can say the voltage clamping device also we can use. Okay, right. So this is the voltage versus impedance characteristic of the varistor, okay, right. Next is overcurrent protection. So in order to protect the SCR against overcurrent, yes, what we are doing, we are using fast acting current limiting fuse, FACLF, and circuit breaker, and circuit breakers are used. FACLF means fast acting current limiting fuse, and circuit breakers are connected in series with SCR, Next is high dV by dt protection, For that RC snubber circuit is used, RC snubber circuit. It is connected across SCR. RC snubber circuit is connected across SCR. And high di by dt protection. Yes, inductor is connected in series with SCR. Inductor is used. So you may get a question. Okay, so to protect SCR against over voltage, which of the following device is used? Okay, so for over voltage, varistor. Over current, fast acting current limiting fuse, and a circuit breaker. For high dV by dt, RC snubber circuit, and high dI by dt, inductor is used. Alright, yes. And thermal protection, in order to limit the temperature, because every semiconductor device is having some temperature withstanding capacity. If the device temperature goes beyond that maximum allowable temperature, your device may get damaged permanently. Okay, so we need to limit the temperature. We need to protect the device from temperature or high temperature. So for that, generally we heat sink is used. Heat sink. With the help of heat sink, we are collecting the additional heat which is generated in a device body, and we are throwing that heat to the surrounding. So heat sink is used. Next, apart from the SCR, we need to protect the gate cathode circuit of the SCR also. Okay, so for gate cathode circuit, over voltage protection, over current protection, and protection against noise signals are used. Okay, so over voltage protection, how to protect the gate cathode circuit of SCR against over voltage? So for that, let me write here. Zener diode is used. You might be knowing Zener as a voltage regulator, right? Same thing we are doing here. Second, over current protection. How to protect the gate cathode circuit of SCR against over current? So here small value of resistor is used. Small resistor. Small resistor is used. Right? Small resistor. Here fuse is not required, because in a gate cathode circuit, the current is nothing but your gate current, and that current is hardly in milliampere. Okay, so here current value is less, so that's why only resistor is sufficient. Okay, next, protection against noise signal. So for that, RC filter is used. RC filter is used. Right, RC filter is used. Next, commutation of SCR. Commutation means turning off of a SCR. Commutation means turning off. How to turn off the SCR? That is commutation procedure. So suppose your SCR is in a conduction mode, and if you want to turn it off, so we are having the two requirements. First one is, we need to reduce the current flow through the SCR below the holding current value. And second one is, only reducing the current below the holding current value is not sufficient to turn off your SCR successfully. We need to maintain reverse voltage also across the SCR. Okay, so I am writing here how to turn off SCR. First is, SCR current means anode current should be less than the holding current value. And second requirement is reverse voltage. We need to maintain reverse voltage across SCR. We need to maintain reverse voltage across SCR. All right. Next, which are the different types of the commutation? Natural commutation, forced commutation and load commutation. Okay, natural commutation is possible or used only in the converters or the circuitries where input is AC. So in which converters the input is AC? AC to DC converter, that is a rectifier. Yes or no? Right? Your AC to AC converter, that is AC voltage regulator. Okay. So natural commutation is used in rectifiers. They may frame a question. Rectifiers, AC voltage regulators, AC voltage regulators, and step down cycloconverters. Step down cycloconverters. Okay. So they may frame a question, in which of the following circuitries the natural commutation is used? So in rectifiers, your AC voltage regulators and step down cycloconverters. In step up cycloconverter, forced commutation is used. Be careful. Next, forced commutation. Forced commutation is used in the circuitries where input is a DC. Okay. So suppose you are having the DC to DC converter, that is chopper. Inverter, and step up cycloconverter. Okay, forced commutation is used. Strictly speaking, in choppers and inverters, in practical case, we are using fully controlled devices. But suppose if you use the SCR in a chopper and inverter circuitries, then you need to go for the forced commutation circuitry. Okay. Next, load commutation. Load commutation is possible only if in case of underdamped load. Underdamped RLC load. If load is RLC and underdamped, then only load commutation is possible. Generally, the load commutation is used in the case of inverters, okay, where the load can be RLC. Load can be RLC. Okay. So this is about the commutation of the SCR. Next, thermal modeling of SCR. So regarding the thermal modeling of SCR, here these expressions are important. You may get the questions on these expressions. Okay, on these expressions. So Tj, junction temperature, Tc case, and theta Jc, that is a thermal impedance between junction and case. And similarly, we are having different expressions. So these expressions are important. Series and parallel operation of SCRs. So regarding series and parallel operation of SCRs, the important things: string efficiency for series connection, string efficiency for parallel connection. Okay. So please go through these expressions. These expressions are important. Next, other switching devices are triac. Yeah. So here it is the construction of a triac. As long as if you refer the previous year questions on construction of the triac, they have not asked the question. Okay. So this is a symbol of a triac, and triac is equivalent to the anti-parallel connection of two SCRs. It is equivalent to anti-parallel connection of two SCRs. In triac, we are having the terminals MT1, MT2 and gate. We don't have anode and cathode. Be careful. MT1 means main terminal 1, MT2 is a main terminal 2 and a gate terminal. Okay. The VI characteristic of a triac, yes, it is in a first and the third quadrant. First and the third quadrant. Highlighting points about the triac. So triac is a bipolar switch. It can block forward voltage as well as reverse voltage during its off state. It is a bidirectional switch, right? Bidirectional switch. It is a current controlled device. Triac is a current controlled device. Yeah, so these are the important points regarding the triac. Next, GTO, gate turn off. GTO construction is similar to that of your SCR. Okay, right. But it is a fully controlled device. Means we can turn on the GTO by circulating the positive gate current, and we can turn it off by circulating the negative gate current. Okay, right. But generally, the required value of the negative gate current to turn off the GTO is high. So that's why GTOs are not popularly used. Okay, so construction of the GTO. And symbol, there are three valid symbols for the GTO, right? Anode, cathode, gate. This is the first symbol, second symbol and third symbol. These are the three valid symbols. In one of the examination they ask the question based on the symbol of the GTO. Okay, so please go through it. Okay, right. Next, VI characteristic of GTO is same as that of your SCR, same as that of the SCR. Check VI characteristic of SCR and this GTO, both are same, both are same. Highlighting points regarding the GTO. GTO is a fully controlled device. Yeah, before that applications. We are using GTOs in inverters, uninterruptible power supplies, motor drives, electric traction drive systems. Highlighting points, it is a fully controlled device. We can turn it on by using positive gate current, we can turn it off by using negative gate current. So it is a fully controlled device. Okay. Next, it is a bipolar switch like your SCR. It is a unidirectional switch like a SCR. Okay. And it is a current controlled device. Gate current is used to control the device. So it is a current controlled device. So GTO is similar to that of your SCR. The only difference is your SCR is a semi-controlled switch, GTO is a fully controlled switch, right? Yeah. Yeah, 4 layers and 3 junctions, okay. Power BJT, bipolar junction transistor, power BJT. So it is a construction of the BJT. In BJT we are having the different layers like collector, emitter and a base. If you compare collector, emitter, base, this base layer is having a comparatively less doping, right? Symbol of the BJT, similar to that of your signal level BJT. Signal level BJT means whatever the analog electronics you have studied. In analog electronics also you are having the BJT, na, right? So power BJT symbol is same as that of your analog electronics BJT, okay, right? VI characteristics of the BJT. So there are 3 regions: saturation, active region and cutoff region. This is cutoff, active region, and here it is a saturation region. In power electronics we are operating BJT only in cutoff and saturation region, only in cutoff and saturation region, okay, because we are using this as a switch, na, so we want switch either in a on state or off state, okay, like this. Highlighting points about the BJT. BJT is a unipolar device, it is a fully controlled, it is a current controlled, it is a fully controlled. Base current controls the BJT's operation. Next, it is a unipolar device, okay, it can block high value of forward voltage, high value of forward voltage. Be careful, here we are having bipolar junction transistor, right? But it is a unipolar device, because in power electronics we are dealing with a high value of voltage, and your power BJT can block high value of forward voltage. It cannot block high value of reverse voltage, okay. Very small value of reverse voltage it can block, hardly 40 to 50 volt it can block. Next, it is a unidirectional switch, and it is a current controlled device, yes, same. IGBT, insulated gate bipolar transistor. So basic structure of IGBT. It is a 3-terminal device. 3 terminals are emitter, collector and gate, okay, right. Symbol of IGBT, here it is a symbol of IGBT, gate, collector and emitter. It is a voltage control device. Which voltage controls the IGBT's operation? VGE, voltage between gate and emitter. It will control the IGBT's operation. VI characteristic of IGBT, it is like your same BJT. Yeah, some applications of IGBT you can simply go through it. If you want these PPTs or the notes also, okay, at the end I will give my contact number and mail ID. If you want the notes and these PPTs you can message me, okay, right. Highlighting points of IGBT. IGBT is a fully controlled device, right. It is a voltage controlled, it is fully controlled. Fully controlled means we can turn on the IGBT by using the voltage, and we can turn it off by using the same voltage, okay. So that's a fully controlled. IGBT is a bipolar switch. It is a unidirectional, sorry, IGBT is not a bipolar, it is a unipolar, please correct that. It is a unipolar. IGBT is a unipolar. IGBT is a voltage controlled device. Yeah. Next, power MOSFET. Here it is a VI characteristic of a power MOSFET, right? MOSFET is also voltage controlled device, okay? Like your IGBT. There are some of the applications. Yes, these points are important. It is a fully controlled device, MOSFET. It is a unipolar device. Unipolar means it can block high value of forward voltage only, no reverse voltage blocking. It is a unidirectional device. This is a voltage control device like your IGBT, okay? IGBT is also voltage control. Yeah. And during on state, MOSFET is like a pure resistor. During on state, BJT is like a pure voltage source, constant voltage. During on state, MOSFET is like a pure resistor, Yeah. Yeah. So these are the some of the points regarding the chapter number 1. Now we are going to discuss some questions, okay? Right. Let us discuss this question, some simple questions, only diploma level. Which semiconductor power device out of the following is not a current triggering device? Come on, tell me. You can post your answers in a chat box. Simple question. Which semiconductor power device out of the following is not a current triggering device? Come on. Out of these 4, which is not a current triggered? Come on. Not a current triggered, huh? He is asking about not a current triggered. Yes, can anyone? You can post your answers in chat box. Yes. Yeah, Raja is saying B. What about others? Yes. Not a current triggered. Tell me, yes, thyristor. Thyristor means SCR. SCR is a voltage triggered, na? SCR is a current triggered, sorry, not a voltage, it is a current triggered. Current triggered, or you can say current controlled. Which current controls the SCR's operation? Gate current, okay? So SCR is a current controlled. What are the MOSFET? MOSFET is a voltage controlled. Alright? GTO, gate turn off. GTO is also current controlled. Gate current controls the GTO's operation. Triac is also current controlled, no? So if you check, he is asking which of the following is not a current controlled. So answer should be option B. MOSFET is not a current controlled. Okay, MOSFET is not a current controlled. Right. Next simple question. Which semiconductor device behaves like 2 SCRs? Come on, just now we discussed. Out of these 4, which semiconductor device behaves like a 2 SCRs? Yes. You can post your answers in chat box. Yes. Yeah. We know not triac. Triac is equivalent to anti-parallel connection of 2 SCRs. Okay. So answer is a triac. I am writing here. Triac is equivalent to anti-parallel connection of 2 SCRs. Okay. Anti-parallel connection of 2 SCRs. So here answer is option B, triac. All right. Next, yeah, this is a standard question. You can check in ESC examination, he asked this question. In your Genco Transco, okay, after BTech you are having the Genco Transco recruitment. In that examination also he has asked a question, and also in your diploma level also he has asked this question. Okay, so 3 times in GATE examination also he has asked this question. So in 4 examinations almost this question is repeated. Okay, yeah. If the amplitude of the gate pulse during turn on of an SCR is increased, then what is happening to the delay time and the rise time he is asking. Okay, so always keep in mind, if the forward voltage is kept constant and while turning on the SCR, if the gate current is increased, then delay time decreases, but your rise time will not getting affected, because the rise time depends on your load. Rise time depends on load. I am writing here, rise time depends on load. And delay time decreases. With the increase in gate current. With increase in gate current. So if gate current increases, your delay time will decrease, but rise time will not be getting affected. So if you check the options, delay time would decrease, but rise time would not decrease. Okay, delay time would decrease while the rise time remains same. Option D is the correct option, right? Option D is the correct option. Yes, so important question, one of the important question. Next, which statement is true for latching current? Come on, post your answers in chat box. Just now we discussed the latching current and holding current. Okay, so tell me the answer. Simple question. Yeah, Omkareshwar is saying, sir, in on state, how many junctions conducted? Yeah, Omkareshwar, please keep in mind, if SR is in a conduction mode, that is SR is in a on state, then all the 3 junctions will be in a forward bias mode. Okay, always keep in mind, not only in SR or in any of the semiconductor devices. If your semiconductor device is in a on state, then all the junctions will be in a forward bias mode, or all the junctions will be in a conduction mode. All right, yeah, yes, yeah, yes. Which statement is true for latching current? Latching current is related to turn on of SR, na? So option C is the correct option, right? Option C is the correct option. Yeah, it is related to turn on process of the device. All right, next, thyristor can be protected from over voltage by using, yeah, just now we discussed. For over voltage protection, yes, varistor is used, but in the option varistor is not given. So tell me the suitable answer. Voltage clamping device, fuse, heat sink, snubber circuit. Tell me, for over voltage protection, can we use fuse? No, fuse is for over current, na? Next, for heat sink is for to limit the temperature, that is protection against the temperature. Next, snubber circuit is for dV by dt protection. dV by dt is a different thing, over voltage is a different thing, be careful. Okay, so here voltage clamping device, voltage clamping device. Voltage clamping device means you might be knowing the clamper, clipper and clamper in analog electronics. Okay, so voltage clamping device means it is a device which will not allow the voltage across the device to become greater than its rated voltage, right? Greater than the rated voltage means it will clamp the voltage. So correct answer is option A. Option A is the correct option. All right, next, the triac is equivalent to, yes, we discussed, 2 SCRs connected in parallel, no. 2 SCRs connected in anti-parallel, yes. Okay, triac is equivalent to 2 SCRs connected in anti-parallel. 2 transistor model of a thyristor consists of following 2 transistors. Come on, in a 2 transistor model of the thyristor or 2 transistor analogy we discussed just now, right? In that your SCR is SCR consists of which 2 transistors he is asking. Yes, correct answer is We know na PN device structure is divided as PNP and NPN na, right? So correct answer is one is PNP and second one is a NPN na, right? NPN and PNP, NPN and PNP. All right, option A is the correct option. Look, very simple questions they have asked, right? Very simple questions. Next, LASR has, LASR means light activated silicon controlled rectifier. Okay, so I am drawing here the construction or the structure of LASR. Right, this is the construction of the LASR. LASR stands for light activated silicon controlled rectifier. Light activated silicon controlled rectifier. Yes, in LASR the gate terminal is absent, but instead of gate terminal generally a recess is provided here. Means when you strike a beam of light here, then this device will start conduction. Okay, now he is asking in LASR how many layers and how many junctions are there. Yes, tell me. P1 N1 minus, this is a one junction. N1 minus P2 junction second, P2 N2 plus junction J3. Okay, so LASR is also having the 4 layers and 3 junctions. 4 layers and 3 junctions. So option A is the correct option, right? Option A is the correct option. Next, the number of PN junctions in a thyristor is, yes, very simple question. How many PN junctions? 3. Which one of the following is a bidirectional controlled device? Switch or the device? Bidirectional he is asking, and controlled also. Bidirectional and controlled. Okay, be careful. So thyristor, whether thyristor is a bidirectional? No, thyristor is a unidirectional. Triac is a bidirectional. And triac is a controlled? Yes, we can control the triac operation by using the gate current. Na? So triac is a controlled as well as bidirectional. GTO is a unidirectional. What about the diac? Diac is also bidirectional, but it is not controlled. Yes or no? Right? It is a bidirectional but not controlled. Be careful. So he is asking bidirectional and controlled. So your answer should be option B, that is a triac. That is a triac. Alright. Next, once SR starts conducting a forward current, its gate loses control over. Come on, tell me answer. You can post your answers in chat box. Yes, you can post your answers in chat box. Once SR starts conducting a forward current, its gate loses control over. Means once SR is in a conduction mode, then my gate current will lose the control over anode voltage, anode current, anode voltage and anode current, anode voltage and time. Yes, can anyone? Once SR is in on state, then yes, gate current loses control over anode current only, because SR is in on state, then your gate current and anode voltage is not having any relation. Okay, right? Only control over anode current, control over anode current. Next, because when SR on state, the voltage across anode and cathode of the SR is very small, that is a on state voltage drop. Okay, right. Next, Pick the voltage control devices from the following. From this, which are the voltage control devices? MOSFET and IGBT, na? Right? Other you can check, MOSFET is a voltage control, GTO current control, IGBT voltage controlled, SCR current control. Third option, SCR and GTO. SCR and GTO both are the current control, na? Right? So here voltage controlled means MOSFET and IGBT. MOSFET and IGBT. Alright? The voltage across a SCR is found to be 68 volt and current is 0.01 milliampere. Now the device is, yes, tell me. We discussed the static VI characteristics of the SCR. From that we know we are having the three modes, na? Forward blocking, forward conduction, reverse blocking. So this question is related to VI characteristic. Okay, yeah. It is given that voltage across SCR is 68 volt and current flow through device is only 0.01 milliampere. That is very, very small current. So voltage across device is a positive and high voltage and current flow through device is very, very small. 0.01 milliampere means it is only leakage current. So tell me, out of these four, which option will be correct? Voltage across device is a high voltage and it is a positive voltage, huh? And current flow through device is very, very small, leakage current is there. So mode of operation of device will be, yes, can anyone? Positive voltage means device should be in a forward bias mode. Device should be in a forward bias mode only. No reverse bias. Huh? Reverse bias means voltage across device is negative. So here voltage positive means device forward bias. And current is only leakage current, na? Means device is in a on state or off state. If current flow through device is very, very small, leakage current is flowing, means your device is in a off state. Device is in a off state. Right? So correct answer is option A. Forward biased and turned off. Forward biased and turned off. So be careful, huh? Right. Cutoff region, negative resistance region and saturation region are regions in volt ampere characteristic of. So in which of these devices VI characteristic, yes, these regions are present. Cutoff, saturation and negative resistance. Negative resistance region is present only in case of unijunction transistor. Please refer the VI characteristic of UJT. Okay, in that we are having the negative resistance region as well. But whereas all other devices there is a no negative resistance region. Okay, right. So correct answer is option A. When cathode of a thyristor is made more positive than its anode, then yes, cathode is more positive than the anode. Means your device is in a reverse bias mode. If device reverse bias mode, then outer junctions are forward or reverse bias? Reverse bias. Outer junctions are reverse bias. But what about the central one? That is middle junction, forward bias. That is J1, J3 reverse bias, J2 forward bias. It is given that your SCR is in a reverse bias mode. Cathode is at a higher potential than that of the anode. Okay. So I am writing here J1 and J3 are in a reverse bias mode and J2 forward bias, right? J2 forward bias, J1, J3 reverse bias, right? J1, J3 reverse bias. So outer junction, J1, J3 means J1, J3 are the outer junctions, right? J1, J3 are the outer junctions and J2 is a central one, na? So forward bias, reverse bias. Alright, next. The snubber circuit is used in thyristor circuit for, yes, very simple question we discussed. Come on, post your answers. Snubber circuit is used for dV by dt protection, na? dV by dt protection, right? Capacitor and resistor. Capacitor is generally used, capacitor function is, capacitor is the element that opposes the sudden change in voltage, na? Right? So please understand this, dV by dt means we are interested in opposing this rate of change of voltage with respect to time. So for opposing the rate of change of voltage with respect to time, a capacitor is connected. but only connecting the capacitor is not sufficient. A resistor is also required. The function of resistor is, it is required to limit the discharging current of the capacitor. Okay, in that much depth you don't have. Okay, the concepts, only RC's number you can write, that is sufficient. Okay, that is sufficient. Next, so here correct answer is option B. Option B is the correct option. In an SCR, if latching current is IL and holding current is IH, then the following relation hold good. Good is in the sense it is a valid or a true. Yes, if you check IL and IH, which current is greater? IL is greater than IH, na? IL is greater than IH. Option D is the correct option, right? Which one is the most suitable power device for high frequency greater than 100 kilohertz? Yes, we discussed if frequency is greater than 50 kilohertz, only one option we are having, that is power MOSFET, right? Power MOSFET. Look, very simple questions, huh? But these are the informative questions, huh? Right? Yeah. In a transistor, which of the following layer is lightly doped? Yes, in transistor means your BJT. In BJT, which layer is lightly doped? Base layer is lightly doped, na? Right? In BJT, we don't have the drain layer, huh? Be careful. We are having only 4 layers: emitter, collector, drift layer and base layer. But here he has written drain. Drain layer is not present in BJT. Okay, so lightly doped is your only base layer. Base layer is a lightly doped. If the gate current of an SCR is increased, its forward breakover voltage VBO will, recall the VI characteristic of the SCR. As the gate current increases, the breakover voltage decreases, VBO decreases, right? More the gate current, lesser will be the breakover voltage of the SCR. Yeah, so these are some of the points related to the chapter number 1. Now we are going to discuss the second chapter, AC to DC converters. Okay, right? It is also known as a rectifiers. So if you check, most of the questions they have asked on the second chapter, more weightage for the second chapter. In any of the examination, comparatively chapter number 2 is having more weightage, huh? And the chapter is vast also. Okay, right? Yes, let us discuss some important points. Have a look. So AC to DC converters, in that we are having the controlled rectifiers and uncontrolled rectifiers. Okay, right? So phase controlled converters or rectifiers are having 2 types: single phase converters and 3 phase converters. In a single phase, again there are 2 types: uncontrolled converters, controlled converters, and 3 phase uncontrolled converters and again controlled converters. Okay, uncontrolled means the converters or the rectifiers where only diodes are used, and controlled means the converters where SCRs are used or rectifiers where SCRs are used. Alright, next. So based on the number of pulses, so this is a general classification, right? In addition, we are having based on the number of pulses of output voltage waveform, we are having the various types like single pulse rectifier, 2 pulse rectifier, 3 pulse rectifier, 6 pulse rectifier and 12 pulse rectifier. Okay, single pulse rectifier means it is the rectifier which gives only 1 pulse in the output corresponding to the 1 input cycle of the supply, right? Means when your supply completes 1 cycle, then your output will be having only 1 pulse in the output. So it is known as a single pulse rectifier. Like your half wave rectifier. Half wave rectifier is also known as a single pulse rectifier. Is also known as a single pulse rectifier. Next, a 2 pulse rectifier. In a 2 pulse rectifier, for 1 cycle of the input, we are getting 2 pulses in output, right? So if you recall, in a single pulse rectifier, my output is like this. This is omega t and my V0. 0 to pi it is non-zero and pi to 2 pi it is a 0, right? And again 2 pi to 3 pi, again we will be getting the positive half cycle. Okay, okay, right? So this is the output I am getting for single phase, single pulse, that is half wave rectifier. Whereas in full wave rectifier, how is my output voltage? In full wave rectifier, output voltage is like this. We are getting 2 pulses na, for 1 input cycle. So this is a 2 pulse, okay, 2 pulses for one input cycle. So next, 3 pulse rectifier. 3 phase rectifiers will give 3 pulses in output for one input cycle. Okay, so 3 phase half wave rectifier, if you recall output voltage waveform of 3 phase half wave rectifier, we are getting 3 pulses for one input cycle. Okay, next one is 6 pulse rectifier. 3 phase full wave rectifier is also known as 6 pulse rectifier, and similarly we are having the 12 pulse rectifier. 12 pulse rectifier is not there in your syllabus, so forget about it. Okay, right, yes. Next, so single phase uncontrolled converters or rectifiers are again having 2 types, half wave, full wave. 3 phase also having half wave, full wave, and here it is 12 pulse converter. Okay, 12 pulse is not there in your syllabus. Yeah, so based on the quadrant of operation, important one. Okay, so based on the quadrant of operation also we are having the various types, that is a 1 quadrant converter, 2 quadrant converter, and 4 quadrant converter. They have asked the question, which of the following converter operates in only first quadrant? Which of the following converters operates in the first and fourth quadrant? Which of the following converter operates in all the 4 quadrants? Okay, so these are important, please be careful. So here, based on the quadrant of operation, specifically these quadrants of operation are defined by considering the load on the converter as a DC motor. DC motor load means what? RLE load. Okay, RLE load. Okay, right. So here we are having the 3 types. 1 quadrant, that is a single quadrant rectifier. Single quadrant rectifier. Single quadrant rectifier means these are the rectifiers which gives output voltage and output current as a only positive. As a only positive means these converters operates in only first quadrant. Output voltage is positive, output current is also positive. And which converters gives this type of output? Yes, we are having the converters, all the uncontrolled rectifiers, all the half controlled. Half controlled means what? Semi converters na? Half controlled or semi converters all operates in the first quadrant. So be careful, uncontrolled rectifiers and your semi converters gives only first quadrant operation. Only first quadrant operation. Next, 2 quadrant operation. 2 quadrant rectifiers or 2 quadrant operation. So which rectifiers gives the 2 quadrant operation? 2 quadrant means yes, output voltage can be positive as well as negative, but output current is only positive. So your single phase fully controlled rectifiers, or it is also known as full converters, these operates in first and fourth quadrant. These operates in first and fourth quadrant. If you recall, in a semi converter, how is my V0 average? In semi converter, V0 average is proportional to 1 plus cos alpha na. Alpha means what? Firing angle na, right? So if you vary the firing angle from 0 to 180 degree, my output voltage is always positive, right? And your rectifiers will give output current as only positive. Okay, so therefore first quadrant operation. But whereas in a full converter, if you check, your output voltage is proportional to cos alpha. If output voltage is proportional to cos alpha, if alpha is less than 90 degree, cos alpha is positive, means output voltage is positive. If alpha is greater than 90 degree, cos alpha is negative, output voltage is negative. So we can achieve positive voltage as well as negative voltage by using these converters. Okay, so full converters operates in first and fourth quadrant. Semi converters operates in only first quadrant. Next, dual 4 quadrant operation. 4 quadrant operation means the converter which gives the output voltage as well as output current positive as well as negative. So we are having the dual converters. Dual converters operates in a 4 quadrants. Dual means what? Dual means 2 na. In dual converter, what we are doing? In a dual converter, 2 full converters are connected. 2 full converters are connected in anti-parallel anti-parallel. Dual converter means what? It is simple anti-parallel connection of two full converters. So dual converter, 4 quadrant operation. Full converter, first and fourth quadrant operation, that is 2 quadrants. And semi converter, only 1 quadrant operation. Alright. Yes, now let us discuss some simple circuitries. Single phase half wave uncontrolled rectifier with resistive load. You might have come across this type of circuitry. Okay, uncontrolled rectifier. So uncontrolled means diode is present. Okay, input is a AC load. We have considered the resistive load. Okay, I am not going to discuss the circuit operation here because it is only revision series, right? Yeah. So when Vs is positive, what will happen? Supply voltage is plus here, minus here. Diode will be in a forward bias mode. Your diode will start conduction, current will flow like this. Okay, so my output voltage waveform, please be careful. This is supply voltage waveform, which is Vm sin omega t. Output voltage is this type of pulse we are getting, right? And output current is also in phase with the load current, in phase with the load voltage, okay? As long as diploma level is considered, voltage across diode, this waveform is not required for your preparation, okay? Right? Don't worry, you will not get the question on this voltage across diode waveform, but output voltage waveform is important for you, right? Yes. So when Vs is positive, diode will conduct, current will flow like this. Similarly, when Vs is negative, what will happen? That is pi to 2 pi. Supply voltage polarity is reversed, na? Vs negative means supply voltage polarity is reversed. That is minus here and plus here. Diode will be in a reverse bias mode. Diode will not conduct. So my output voltage, output current will be 0, right? So you can check for one input cycle of the supply, 0 to 2 pi, my supply is having one cycle, na? In the output, how many pulses we are getting? Only one pulse we are getting. Only one pulse. So that's why it is also known as a single phase, single pulse rectifier. One pulse or single pulse rectifier. Alright. Next, so average output voltage. So expression is important. What is V0 average? You might have come across how to derive the V0 average. It is 1 by 2 pi integration 0 to pi Vm into sin of omega t into d omega t. If you simplify it, you will be getting it as Vm by pi, right? Vm by pi, V0 average. You can simplify it, it is simple, okay? Right. Next, RL load. For resistive load, we are getting this type of waveform. For RL load, what is the difference? For RL load, you will be getting some negative pulse also in output. You can check negative pulse in output, right? So from pi to beta, beta is known as which angle? Beta is the extinction angle. Beta means what? Extinction angle, okay? So for RL load, you will be getting the negative pulse in output. And how to remove that negative pulse? So for that, the freewheeling diode is connected, na? Right? We are using the freewheeling diode. So please understand the difference. For R load, no negative pulse. For RL load, because the presence of the inductor, you will be getting some negative pulse also in the output. So what is the drawback of this negative pulse? Due to the negative pulse, my V0 average decreases. Average value of output voltage, V0 average decreases. Alright? Yeah. So that is the drawback of actually RL load. So that's why generally we are using the freewheeling diode. Okay. So they have asked the question, which of the following is a advantage of a freewheeling diode? So freewheeling diode advantage is output voltage increases and input power factor also increases. We'll discuss as we proceed. Next, RL load with freewheeling diode. For RL load, we are having this waveform. If I connect a freewheeling diode, that is a diode across the load, then what happens? This negative pulse will not come here. Now you can check RL load with freewheeling diode, output voltage waveform, and resistive load, that is R load, output voltage waveform, both are same. I am saying if a freewheeling diode is connected across RL load, then output voltage waveform will be same as that of your resistive load output voltage waveform. Alright? Yes, same. Yes. Yeah. So when freewheeling diode is connected, you will be getting no negative pulse. Next, single phase full wave uncontrolled midpoint rectifier. In single phase full wave rectifier, we are having the two types. One is midpoint rectifier and second one is a bridge rectifier. One is midpoint and second one is a bridge rectifier. The difference, yeah, obviously the circuits are different, that is the one difference, but important thing is PIV, peak inverse voltage. You might have heard the PIV. PIV means peak inverse voltage. Peak inverse voltage means whatever the maximum value of reverse voltage that is appearing across your switch, that is the device. In this uncontrolled rectifier, the switch is nothing but diode. If the control rectifier is there, then the switch is nothing but SCR. Okay, so the major difference between midpoint rectifier and bridge rectifier is the PIV rating in a midpoint rectifier is 2 times Vmax, whereas in bridge rectifier it is Vmax only. They have asked the question, the PIV rating across the switch or of the switch in midpoint rectifier is, it is 2 times Vmax, where Vmax means what? Vmax is the peak value of a supply voltage, because my supply is a AC na, and peak value of that supply voltage is nothing but Vm. Okay, and whereas PIV rating in case of bridge rectifier is only Vm. Here it is 2 Vm, here it is a Vm. Alright, yeah. Next, load is resistive, so you will be getting this type of output voltage waveform. You might be knowing this. Okay, right. So here we are getting 2 pulses na, for one input cycle of the supply. How many pulses I am getting? From 0 to 2 pi, my supply is completing one cycle. And in output, how many pulses? This is the one pulse, this is second pulse na, I am getting 2 pulses. But whereas half wave rectifier, only one pulse, alright, yeah. Next, yeah, this is a bridge rectifier circuitry. Okay, same output voltage waveform we are getting. Output voltage waveform is the same in case of midpoint rectifier as well as bridge rectifier, but in practical case generally the bridge rectifiers are preferred. The reason is, in case of bridge rectifier the required voltage rating of the switch is less, because PIV is different. Okay, less PIV in case of bridge rectifier. Next, single phase half wave controlled rectifier. Yeah, controlled means diode is now replaced with a thyristor. Okay, so in order to turn on the thyristor, we need to apply the gate pulse. Unless and until we apply the gate pulse, your device will not start conduction. Okay, so you might be knowing this type of waveforms. Okay, right. Next, RL load. If load is RL, then again you will be getting some negative pulse. To avoid this negative pulse, a freewheeling diode is connected. Yeah, please listen. Effect of inductive load. For your examination, this type of this information is important, because they ask the only theory questions. Very rarely they have asked the numericals. Okay, so yes, average output voltage V0 reduces. Check if in RL is present, that is inductor is present, then you are getting some negative pulse in output, so average output voltage will reduce, it will reduce. Input power factor reduce, it will reduce. Load current I0 waveform gets distorted and load performance deteriorates. Okay, load performance deteriorates. So based on the first point and second point, they have framed some questions. You can refer previous year question papers. Okay, right. Next, single phase half wave control rectifier, RL load and freewheeling diode. If freewheeling diode is connected, what will be the difference? Yes, no negative pulse. You can check in output voltage, there is a no negative pulse. Okay, right. So advantages of freewheeling diode. Yes, what are the advantages? Output voltage increases, obviously. No negative pulse means average value of output voltage will increase. Second, input power factor can be improved. Yes, input power factor will improve. Load current waveform is improved and performance of rectifier is better. Okay, so these first 2 points, as long as diploma levels consider, these 2 points are important. Okay, right. So freewheeling diode advantage. Yes. Next, midpoint rectifier controlled. Okay, resistive load. Same. Output voltage waveform is same as that of your bridge rectifier. Okay, right. Yeah, controlled one now we are getting. RL, you are getting some negative pulse here. You can check some negative pulse we are getting. Okay. Next, and if bridge rectifier will be present, then same output voltage waveform. For RL, again we will be getting some negative pulse. If freewheeling diode is connected, no negative pulse. Output voltage is same as that of your R load. Okay, so please understand the difference. Please understand the difference. Yes, same points we discussed earlier. Yeah, single phase semi converters. Yeah, now semi converter means semi converter is also known as a half control rectifier. Means in a bridge rectifier we are having the 4 thyristors na, right? Out of the four thyristors in a semi converter, 2 will be the thyristors, remaining 2 will be the diodes. So in semi converter we are using 2 diodes and 2 thyristors, 2 diodes and 2 thyristors. Yes, 2 thyristors, 2 diodes. So there are 2 types of the semi converters or 2 configurations, symmetrical and asymmetrical. So here this is a symmetrical semi converter. Why symmetrical? Because this is the first leg and here it is a second leg. Each leg consists of 1 thyristor, 1 diode, 1 thyristor, 1 diode. So it is known as a symmetrical semi converter. Generally the symmetrical semi converter, if used for RL or RLE loads, RL or RLE loads, and this is a asymmetrical semi converter. Check, first leg 2 thyristors, second leg 2 diodes. So this is the asymmetrical. In symmetrical, 1 thyristor, 1 diode, 1 thyristor, 1 diode. So symmetrical. In asymmetrical, both thyristors in one leg, both diodes in a second leg, both diodes in a second leg. Okay. Now in a semi converters, even though if the load is RL na, your output voltage you will not get the negative pulse, because your semi converters are having inherent freewheeling action present, inherent freewheeling action present. Okay. So what is happening actually, suppose if I remove this freewheeling diode also na, then my semi converter will provide the path for this inductor to release energy through 1 thyristor, 1 diode, 1 thyristor, 1 diode. Please recall the operation, na? Right? Yeah. So only important points I am saying. In semi converters, no negative pulse will be getting in the output. Yeah, asymmetrical, same output. Next, source inductance. Source inductance generally in practical case, the input to the rectifier circuitry is given by using the transformer, and your transformers are having leakage impedances. Recall, we are having primary winding, secondary winding na, and both the windings are having the leakage impedances. Okay, and most of the part of the leakage impedance is inductive in nature. So therefore those effect we need to consider as a source inductance, as a source inductance. So what is the effect of source inductance in a converters or in a rectifiers? Here, because of the source inductance, the output voltage of your rectifier is getting reduced, They have asked the question, right? So this is LS, means source inductance, and here we are having the full converter. What is happening here in this case, if you check corresponding to this angle mu, corresponding to the angle mu is known as the overlap angle. Mu means what? Overlap angle. During this interval, all the 4 thyristors will be in a conduction mode. Check here, during this mu, all 4 thyristors are in a conduction mode. Here, this indicates IT1, IT2 means thyristor T1, T2 current increases, and this one is whatever the current is there na, this decreasing current. This is IT3, IT4. This is IT3, IT4, decreasing current. So if you check, during this overlap angle mu, all the 4 thyristors, that is T1, T2, T3, T4, all 4 thyristor currents are non-zero. Means all the 4 thyristors are in a conduction mode. All the 4 thyristors are in a conduction mode. So during overlap angle mu, if the source inductance is present, then during overlap angle mu, in case of single phase full converter, all 4 thyristors will be in a conduction mode, Yes. So I am getting this type of output voltage. Yeah, yes. So here, same thing, during overlap period, all 4 SCRs of a single phase bridge converter will carry the current. Means all the 4 thyristors will be in a conduction mode. They have asked the question, right? During overlap angle mu, all the 4 thyristors will be in a conduction mode, right? So therefore my output voltage during that particular period is 0. So overall my average value of output voltage will be getting reduced. Yes. Next, input power factor for RL and RLE load. How to find the input power factor for RL and RLE load? So if the load is RL or RLE, then input power factor is equal to displacement power factor into distortion factor. We need to use this expression. Okay, right. So how to find displacement power factor, how to find distortion factor. Okay, so we are having some definitions. Okay, simply you might have come across these type of things. Okay, right. At the end I will give the important formulae, right. Yeah. Next, three-phase uncontrolled rectifiers. In a three-phase rectifiers, we are having three-phase 3 pulse, three-phase 6 pulse, three-phase 12 pulse is not there in your syllabus. Okay, right. So this is the circuit diagram for three-phase half-wave uncontrolled rectifier. Okay, so three-phase half-wave uncontrolled rectifier, it will give you the output, 3 pulses in output like this, corresponding to 1 cycle of the input. This is my 1 cycle of the input is completing here. So if you check corresponding to, this is like a 0 and here it is like a 2 pi. Corresponding to 0 to 2 pi, how many pulses? 1, 2 and third pulse here, remaining part of the third pulse is here. So we are getting 3 pulses. Okay. Each diode conducts for 120 degree. Each diode conducts for 120 degree. I am writing here. Each diode conduct for 120 degree. All right. Yeah. Next, three-phase 6 pulse. So in the output it will give you the 6 pulses. Next, three-phase control rectifier. Same. In a control rectifier again we are having the 2 modes, alpha less than 30 degree, alpha greater than 30 degree. Okay. I don't want to go into that in depth. Okay. Next, load is RL load and three-phase 6 pulse rectifier, R load and RL load. Okay, also three-phase semi-converters. So this is the formula table. Okay, right. I will share this with you. Please message me. At the end I will give the contact number. Okay, right. So these are some important points. Yeah. Next, effect of source inductance. These are the important expressions. But as long as your examinations are considered, these expressions are not important. Okay. Only thing is, they have asked some questions like if source inductance is present, then during overlap angle mu, how many SCRs will be in a conduction mode, etc. Okay. What is the effect of source inductance on output voltage? Your output voltage decreases. Like this simple theory questions they have formed. Okay. Right. Next. Yes, these are the important expressions. Yeah. Yeah, check for three-phase full wave, what is V0 average expression, and for three-phase half wave, what is V0 average expression. Yeah. Yes, let us discuss some simple questions on second chapter. Yeah, the output waveform of full wave rectifier can be. So here he has given the 4 options, and he is asking the full wave rectifier output voltage waveform. Yes, full wave rectifier, how will the output voltage waveform? Yes, option C is the correct. This is of half wave rectifier. This one is half wave rectifier, HWR, half wave rectifier. All right. This is full wave rectifier. Option C is a full wave rectifier. What about option A? Option A is the input voltage, na? Input voltage waveform. And he is asking output voltage. So output voltage waveform is this one, C. Right? Yes. The advantage of using a freewheeling diode with a bridge type AC to DC converter is, yes, freewheeling diode advantage, regenerative braking, reliable speed control, improved power factor, reduce the cost of the system. Yes, improved power factor. Option C is the correct option. In a single phase full converter fed by a source having inductance, source inductance, the number of thyristors conducting during overlap is, during overlap, how many thyristors will be in a conduction mode? 4 thyristors will be in a conduction mode, na? Right? An uncontrolled rectifier implies a rectifier in which all elements are thyristors, in which all elements are diodes, in which all elements are both thyristors and diodes, in which all elements are resistances. Come on. Uncontrolled rectifier implies a rectifier. Yes, you can post your answers in chat box. Simple questions. Uncontrolled rectifier means only diodes, na? Right? All elements are diodes. Option B is the correct option. Yes. When fed from a fully controlled converter, a DC motor driving an active load can operate in. Yes. So this question is related to your quadrants of operation. Yes. Here it is a fully controlled converter, na? We know fully controlled converter operates in which quadrants? 4 quadrants, na? First and fourth. So tell me here modes of operation of motor. First is forward motoring, forward braking, reverse motoring and reverse braking, na? Forward motoring, forward braking, reverse motoring, reverse braking. Yes. Now tell me which modes? Forward motoring and reverse braking. So forward motoring and reverse braking. So option A is the correct option. Alright. Next, the number of diodes that are used in a half wave rectifier and full wave rectifier, bridge rectifier are. Yes, half wave rectifier, how many diodes? Only 1. And whereas full wave rectifier, how many diodes? Bridge rectifier, 4 diodes, na? So 1 and 4. Option B is the correct option. Yes or no? Alright. The average voltage of a full wave rectifier fed from AC source of peak voltage Vm and frequency 50 Hz is. Yes. What is the V0 average? He is asking for which rectifier? Full wave rectifier. So what is V0 average for full wave rectifier? It is 2 Vm by pi, na? So it is 2 into Vm means peak value of supply voltage. Yeah. So it is directly given, na? 2 Vm by pi. 2 into Vm by pi. Option B. Check full wave rectifier. How is my output voltage? Output voltage waveform is like this, na? Right? So for this waveform we can easily derive the V0 average. Alright? So it is 2 Vm by pi. For half wave it is Vm by pi. For full wave it is 2 Vm by pi. Right? Next, in a half wave control rectifier feeding REL load, the range of firing angle of thyristor is. Half wave rectifier he is saying and load is REL. So what is the range of firing angle? It is a 0 to 180 degree for half wave, right? 2 quadrant operation of DC motor can be obtained if it is fed from 2 quadrant operation. If it is fed from fully controlled converter, na? Right? Fully controlled converter. A single diode operates as, yes, single diode can be operated as half wave rectifier, right? In phase control rectification, power factor, yes, power factor, let me write, input power factor. Power factor means input power factor. It is 0.9 into cos alpha. 0.9 into cos alpha. Okay, right. So here, if you check, as alpha increases, cos alpha will decrease. So input power factor will decrease. So yes, decrease with increase in firing angle alpha. Option C is the correct option. Yeah, this is the one expression which is valid for one of the converter. Okay, right. A freewheeling diode is placed across the DC load. Yes, we discussed now, to prevent the reversal of load voltage, to permit transfer of load current away from the source, both 1 and 2. Yes, means it will prevent the negative pulse in output voltage, and also after pi till beta you can check your output current, load current will flow through the diode, na? So second one is also true, 1 and 2. Yeah, the output voltage of a single phase 200 volt semi converter at a firing angle of 0 degree is. Semi converter, how is the output voltage waveform? Yes, semi converter, this is the output voltage waveform for semi converter. So what is V0 average? For this V0 average is 1 by 2 pi integration from 0 to pi Vm into sine of omega t, na? D omega t. So it is equal to alpha, he has given 0 degree, right? So it is equal to Vm by pi. So Vm by pi, Vm is 200 root 2 upon pi, right? Semi converter, right? We'll be getting this type of output. Yes, for semi converter, 2 Vm by pi. So 2 into this. So it is 400 root 2 pi. Right? Option B is the correct option. Yeah. Please go through it. Simple questions, right? Yeah. So friends, I think we are running out of time. Okay. So still I am having some more questions. I am giving my contact details. If you want the notes and these PPTs, you can message me. My number 7387864360. My mail ID. Okay, right. So this is my number, contact number, mail ID. If you want these PPTs and notes, you can message me, I will share. Okay, right. I think tomorrow you are having the examination. So all the best for your examination. Right? Yeah. Thank you. Thanks to all of you.